We want R to be the region bounded below by y equals x and bounded above by y equals x squared plus 1. On the range of values where x goes from -1 to 2. So let's visualize that region. So we see y equals x is here. We see y equals x squared plus 1 is here. So what is y ranging from? The lower value for y would be x, and the upper value would be x squared plus 1. So as we want to do this, what are we going to say? Y is going to start at x, and it's going to end at x squared plus 1. And then we're going to need to have dy come first here in terms of defining our region. Now, what happens to x here? What is x ranging from? Looking at this, what is the smallest x value I ever see? -1. What is the largest x value I ever see in this region? 2. So I sort of think of collapsing this graph only on the x values. And in my mind, I see it from -1 to 2. That's where x is going to range from. So that's our region. If we did the integral of 1 dy dx, that would just give us the area of the region. But typically, we want to find a volume under a surface. So what is the question that I'm asking for? The double integral over r, this is now our region r, of 2xy dA change in width times change in height. I have there change in height times change in width. That satisfies it. So the double integral I'm working with here will be 2xy dy dx. This is what we're going to want to do. That will find a volume, in essence, over that region under that surface. Of course, if any of that surface dips below the xy plane, where z is negative, then that volume would be perceived as negative. So let's go ahead and evaluate this. We're first going to do the inner integral. So the inner integral is the integral as y goes from x to x squared plus 1 of 2xy dy. Now, most textbooks do not write the y here. They just say x to x squared plus 1, and the dy implies that it's a y. I like to put it in for emphasis. As far as we're concerned, y is the variable, so x is a constant. That can be brought to the left of the integral operator as y goes from x to x squared plus 1 of y dy, which will be 2x times y squared over 2 as y goes from x to x squared plus 1. So our inner integral becomes what? You'll notice the 2's cancel nicely. So that's xy squared as y starts at x and y ends at x squared plus 1. So what do we get there for our inner integral? X times y squared. Where does y start? It starts at x. But it ends at x squared plus 1. So we do this value first. So x times x squared plus 1 squared, x times y squared, minus where does it end? It ends here at x times x squared. Let me just clarify that. We're plugging x squared plus 1 in for y, x times x squared plus 1 squared using our fundamental theorem of calculus, minus plugging x in for y, x times x squared. What does that give me for my inner integral? We have x times x to the 4th plus 2x squared plus 1 minus x cubed, which is x to the 5th plus 2x cubed plus x minus x cubed. So my inner integral simplifies to x to the 5th. 2x cubed minus 1x cubed is plus x cubed plus x. So that's my inner integral. Now, what does that replace? That is the entire inner integral. So that's this piece here. We replace what's in red with our inner integral here to evaluate our integral. So our integral is simply going to be the integral as x goes from -1 to 2 of that inner integral, x to the fifth plus x to the third plus x. You'll notice that we have the dx here. So my antiderivative for this is x to the sixth over 6 plus x to the fourth over 4 plus x squared over 2, evaluated as x goes from -1 to 2. So we're going to plug in 2, we're going to plug in -1, and then we will subtract. So we get that the integral is 2 to the 6th over 6th plus 2 to the 4th over 4 plus 2 to the 2nd over 2 minus -1 to the 6th over 6 plus -1 to the 4 over 4 plus -1 squared over 2, which will give me 64 over 6 plus 16 over 4 plus 4 over 2 minus 1/6 plus 1/4 plus 1/2. So 64/6 minus 1/6, 63/6, 16/4 minus 1/4, 15/4, 4/2 minus 1/2, 3/2, which equals 63/4. So that is my solution, that double integral over that region R of 2xy dA equals 63/4. Now let's remind ourselves of what that really means. So here's our region that we're interested in. And we want to see what the volume is under that surface above that region. If it's above, it's considered positive. If it's below, it's considered negative. So here we'll go ahead and draw this. A little difficult to see, but I want you to imagine, if you will, the portion of that surface that is directly over that region. Imagine building blocks and finding the volume of that surface above that portion of the region, as well as the portion that's below, or the part that dips below the axis.